Hello everyone, welcome back to our class. Let's continuously study Chapter 10, Radiation. Section 5, Radiant interchange between gray bodies. The absorptivity of a gray body is less than 1, as we know. So, some radiation striking on a gray body will be reflected back, such as this section. This system, there are two surfaces, surface 1 and surface 2. Radiation from surface 1, E1, striking to surface 2, some of energy absorbed. However, there is some reflection to go back to surface 1. So there is some reflection. For convenient to discuss the radiation each other, we give two new definitions. One is radiosity, J, capital J, is defined as the total radiant energy leaving a body per unit time per unit area. Another definition is irradiation, G, capital G, is defined as the total radiant energy incident on a body per unit area per unit time. Hence, net heat transfer from the body Q equals J minus G times area A, where A is the area of the gray body. The net emissive energy is J equals E plus rho G equals epsilon EB plus 1 minus alpha times G. These two equations, we can eliminate G. We obtain Q equals EB minus J times A over 1 minus epsilon over epsilon equals EB minus J over 1 minus epsilon divide epsilon A. We obtain this equation. Noticeable, alpha equals epsilon. We know the absorptivity equals emissivity for this system. Okay, for surface A1, we obtained Q1 equals EB1 minus J1 over 1 minus epsilon 1 divide epsilon 1 A1. We obtain this equation. Here, we think 1 minus epsilon 1 divide epsilon 1 A1 is a resistance. We call it surface thermal resistance. Very similar electrical circulation, the resistance. That's to say, the gray body has a radiation resistance on its surface. Therefore, emissive power will be decreased, so become smaller. For any two bodies, 1 and 2, geometrical factor x1 to 2 is the fraction of radiation A1, J1, which is intercepted by body 2. That's to say, the body 1 and body 2 heat exchanger Q1, 2 equals A1 x1 to 2 J1 minus A2 x2 to 1 J2 heat exchanger. Continuous equals A1 x1 2 J1 minus J2. So, the resistance due to the geometrical factor can be expressed as 1 over A1 x 1 to 2. Resistance due to the emissivity of surface is 1 minus epsilon over epsilon A. A is the area. So the total resistance equals RT equals 1 minus epsilon 1 over epsilon 1 A1. Here is the surface 1, the resistance, and 1 over A1 x 1 to 2, here is space resistance. From body 1 to body 2, there is some space resistance, plus 1 minus epsilon 2 over epsilon 2 A2. Here is surface 2, the resistance. So here is 3 resistance together. Like this, 3 resistance. One is surface resistance. The middle is space resistance. The last one is another surface resistance. So the total heat flow is Q1 to 2 equals EB1 minus EB2 over RT. RT is the total resistance. Together 3 resistance together. Okay. In the same way, we can do some calculation about the surface system. The very typical surface resistance is closed system, consisted of 2 gray surfaces like this. Is there 3 resistance together. One is surface resistance. The middle is space resistance. Another one is surface resistance. 1, 2, 3. 3 resistance for 2 gray surfaces consist of a closed system. Very typical. Okay, for the figure, 1 minus epsilon 1 over epsilon 1 A1. Another surface resistance, 1 minus epsilon 2 over epsilon 2 A2, respectively, is surface 1, surface 2, the surface resistance. And 1 over A1 x 1 to 2 is the space radiation resistance. Okay, when we understand the resistance together, we can calculate the heat exchanger. Q1 to 2 equals Q1, also equals minus Q2, just equals EB1 minus EB2 over the total resistance. So we obtain this equation. It's very typical equation. I hope all of the students can remember these equations, because this system is very typical. Hence, for any 2 gray surfaces, the radiation heat transfer can be expressed as Q1 to 2 equals EB1 minus EB2 over the total resistance. Total resistance includes 2 surfaces resistance and a space heat resistance. So it is 3 resistance together. EB1, J1, J2, EB2. Here is a series system, series resistance system. Okay, the radiation heat transfer is very important. The next several pages, we will discuss several very famous examples. Example 1 is 2 infinite parallel plates like this. Here is 2 plates, parallel plates. Because these plates close to each other, very close. So A1 over A2 close to 1. So x1 to 2 equals 1 also equals x2 to 1. So the heat exchanger Q1 to 2 equals sigma times T1 power force minus T2 power force times A1. A1 is the area. Over divide 1 over epsilon 1 plus 1 over epsilon 2 minus 1 is this equation. This equation is very famous. So I hope students can remember this equation. Example 2, a small body in a big space. This body is no concave, is a ball. In this case, because A1 over A2 is very similar 0, close to 0, because A1 is very small. So x1 to 2 is 1. So Q1 to 2 equals epsilon 1 sigma times T1 power force minus T2 power force times A1. Here is A1. A1 is the small body, the surface. Here is another example. The third one is insulating sheet. The picture like this, the left picture is before inserting sheet. This system is after inserting a sheet. In this system, we can do some calculation about heat transfer. Okay. Before inserting the sheet, we very easy to calculate the heat transfer. We know there is one surface resistance, another one surface resistance. In the middle, there is one space resistance. So it is 3 resistance series together. EB1 to J1 to J2 to EB2. Here is before inserting the sheet. However, after inserting sheet, the system becomes more complex because there are 2 space resistance. Also, there increase 2 surfaces resistance. So the resistance series like this become 6 resistance together. 1, 2, 3, 4. 4 surface resistance and 2 space resistance together. So become more complex. Okay, because the plate is infinite, very big, also is parallel. The geometrical factor is x1 to 3, x2 3 to 1 equals x1 to 2. All of the geometrical factor is 1. Also A1, A2, A3 is same, is A. So before inserting sheet, the heat transfer is this equation we obtained. After inserting the sheet, the resistance becomes 6 resistance. So Q1, 3, 2 equals Q1 to 3 equals Q3 to 2 equals sigma B times T1 power force minus T2 power force times A. A is area. However, over become 6 terms. 1 over epsilon 1 plus 1 over epsilon 3, 1 minus 1 plus 1 over epsilon 3, 2 plus 1 over epsilon 2 minus 1 become 6 terms. Obviously, Q1, 3, 2 smaller than Q1 to 2. Become smaller. If epsilon 1 equals epsilon 3, 1, epsilon 3, 2, epsilon 3, 2 is same. emissivity is same. In this case, we find Q132 equals half of Q122, becomes smaller, only half. With the same way, inserting N sheets between two infinite parallel plates with same emissivity, the heat transfer is Q1N2 equals 1 over N plus 1 times Q122, just become smaller. To increase the insulation effect, the low emissivity sheet should be used. Okay, here is the inserting sheet. We know inserting sheet to decrease the heat transfer is okay. Okay, the section 6, Lambert's law. We know most of the surface do not emit radiation strangely in all directions. We know the black plate emitted its energy to half space. However, it is not the same in all directions. We know the greater part of the energy emitted in a direction normal to the surface. In normal to the surface, the direction is transient. So the rate of the energy emission from unit surface area through unit solid angle, because why here we use the solid angle? Because the surface emits its energy is in half space, in any direction, but the normal direction is biggest. So the emit intensity of radiation in any other direction at any angle to the normal, like this. In the normal direction, the intensity is biggest, but in this direction, certainly becomes smaller. Here, the Lambert's law tells us in this direction, the intensity, if we use I phi to express it, equals In cosine phi. Phi is the angle. This equation, we can call it Lambert's law. But for plate, most cases we use the solid angle to calculate. So Lambert's law is a little simple. Okay, the section 7, selective emitters. As we know, when the source the temperature and receiving surface the temperature is the same, the absorptivity and the emissivity is the same. Just alpha equals epsilon. But in practice, the absorptivity of the surface will change with the temperature. When the temperature is changing, the emissivity or absorptivity is changed. If it changes considerable with the temperature, we can call the surface is selective emitter surface. For example, like this, the horizontal axis is temperature. The vertical axis is absorptivity. We can find for white phi clay, the absorptivity decrease very fast. Aluminum, maybe there is a little increase. Just to say, the absorptivity is changed with the temperature. We have learned for a body with absorptivity alpha, we use E equals alpha EB to calculate a practical surface, the emissive energy or receive the energy. Also, we use E equals alpha sigma T power force to calculate. Here the EB is the radiation energy from surface, E is the receiving energy. On the other hand, for any practical body, we have E equals epsilon sigma T power force. So this equation and that equation, there is a condition, is the temperature is same. In this case, epsilon equals alpha. Kirchhoff's law tells us. However, the industrial area, many cases is different like this. For example, in solar energy application, most of the cases we use the selective coating because the solar light comes from surface of the sun. But the receiving area, the temperature may be only 400 Kelvin. It's different because sun surface, the temperature is 5,700 Kelvin. It's different, very big the difference. So in this case, in the wavelength is very, very small. The receiving area, also the absorptivity is very big. However, in the large wavelength range, the absorptivity is very small. So in this case, the absorptivity is changed. In this case, we use selective coating to increase the receiving energy. Thank you very much.